is that gonna be on the test?
Okay, so this one from your guys' notes sheet,
Note sheet?
your packet, activity packet,
Oh, okay.
has a drawing of a circuit. It's got two resistors and an inductor in it. The switch in the figure is initially open. Find the current in R2 immediately and a long time after the switch is closed.
This one?
Long after the switch is closed, it's reopened. Find the current in R2 immediately after the second switch opening.
Activity. Was it online?
I don't,
With the homework?
no, it's all part of the worksheet.
Oh, ooh.
That's me.
There.
Okay, so that's our switch, or our circuit.
Circuit.
So the first thing is, I guess we'll do part A and part B, even though it's not labeled as such. Find the current in R2 immediately after the switch is closed. So that's the first thing we'll do. Find I in R2 at time equals 0. So tell me logically what's going to happen in the circuit when I close the switch at time equals 0.
Seems like a lot of,
Lot of current will be going through, but none of it will be going through L.
Right.
And all of it will be going through R1 and R2.
All right, yeah, exactly. So time equals 0. The current tries to be rising.
but it can't go anywhere.
Because that poses all of it, right?
Yeah.
Yeah.
This guy says, nuh-uh, not happening. And so at time equals 0, this is our logic. L, I should say this is what blocks it. The induced EMF blocks I through L completely. Okay, so we have our effective circuit then. Looks like the inductor's not even there because it's not allowing current to go that way.
Right, so it's just going through those two. In a series.
So if you wanted to solve for the current through R2, what would be your method
So just add.
without an inductor? Like using just this circuit, how would we find the current?
E over R1 plus R2.
That's what I was
Okay,
thinking.
and so how did you get that, Derek?
Ohm's law.
Okay, so from
I love just throwing out a lot. Yeah, a lot.
using some of the things we did in class to kind of get that, for those of you who haven't
In series.
done this a lot of times. We use Kirchhoff's voltage law and walk our way around the circuit. Or we called it loop rule. That's
Loop
easier than
rule.
writing Kirchhoff's name.
KVL.
KVL, PCL.
Kirchhoff's voltage law. That works better. Okay, so E minus IR1 minus IR2 equals 0. And then solving for E, we have I R1 plus R2. Solving for I, we have E over R1 R2. R1 plus R2. So that's what Derek said. We don't have any numbers, so that's it. That's the answer. So any questions about that part? Okay. Oh, I guess for room's sake, I'll do part B right here. There's no B, but whatever. So find I through R2 at time equals infinity. So the switch has been closed for a really, really, really long time. Someone tell me what happens.
Acts like the inductor acts like a short.
Okay, the inductor acts like a short. So what does that mean as far as the currents in the circuit?
Well, it's gonna
Dissipated.
start going
It's
through
all-
the E,
isn't
the
it?
L, isn't it? It's
Yeah,
gonna start going through there.
but it goes through there like what?
So it's,
Like
Well,
gangbusters, right?
Yeah.
It's got no resistance, and this isn't something we've really talked about before. But
So just
if
skip
current
R2.
has the option of going down a path with resistance or going down a path with 0 resistance.
Well,
It'll take
obviously.
the
Yeah, it's
least
not gonna go
resistance.
down the path of the resistor at all, it just says why.
Will it try to and then change?
No.
No, okay.
Just doesn't.
If there's no resistance on the other one, it'll
It's
just
like
strictly-
water.
Right.
It takes the path of least resistance.
Right.
Yeah, it'll all just go down the inductor in that case, so it's like the opposite of that. In time equals 0, none goes down the inductor, time equals infinity, all of it goes down the inductor. Okay, so if none flows through R2, what's the current through R2?
E to the
Zero.
power 1.
0.
Ah. Plug those numbers in.
Yeah, that's just.
Okay, any questions then about these two conditions on our rising current for this circuit? No, okay.
So far, so good.
So far, so good. Then a long time after the switch is closed, it's reopened. Find the current in R2 immediately after the switch opening. So part C, switch opened. So what does that mean? Are we?
That means that there's no more added to it, there's just whatever's in there.
Current
Yeah.
is decreasing.
So we're
Right,
we're in
and
the
then-
falling current.
Falling.
Falling current.
Yeah. And so at time equals 0, find I through R2.
Plus.
So somebody want to talk verbally about what's going to happen at time equals 0?
R1 gets taken out of the equation entirely, so you only have the two elements.
Good.
R2 and the inductor.
Okay. So we have a new effective circuit.
So the R goes away.
And what is the direction of the current in this loop? Still clockwise? Yeah, so it stays in the same direction that it was going before. So, what else is important for us to note about how they worded this? When they say, long time after the switch is closed, it's reopened.
Then it's possibly have gotten to its max.
It's.
There we
yeah.
go, yeah. So the initial current going through this loop, I naught is equal to I max. Okay.
There are moments I actually can.
So then we have to figure out what was I max.
E over R.
E over R1.
Okay. So, why? Someone want to tell me why? So I max equals E over R1.
Because R2 wasn't in the circuit when it was charging it. Whatever.
It wasn't?
Well, it was,
Oh, in this case, right
Yeah.
after time equals 0.
Yeah.
Okay, then it
Yeah.
was just this loop. Okay,
Excuse me.
so when it reached maximum current.
yeah, while it was
Oh,
doing
yeah.
all that, it
Yeah,
it
then
had
this
R1
one.
involved and R2 not involved.
Yeah, okay,
And
so,
we're talking about like immediately after that?
okay, I will erase all this because we won't need this. So when the rising current reached maximum value, R2 was not part of current flow. So our effective circuit in that case, actually no, it was like the short, right? There's,
Bare wire.
okay. And so in that case, this was our I max value, and then I max is just R1 over, nope, E over R1. Okay. All right, so any questions about that? You guys gave some very helpful explanations for what was happening in each state. So I like this problem
Oh, is
because,
this another possible testing?
yeah, yeah, because this is like mostly just logic. I mean, we're using some of our equations from the past, but nothing, not having to use the complicated exponential equations. We can really just logic our way. And I know, Lena, you like problems where you can just write a paragraph explanation. I kind of do too. So in this case, like for each one, you can say, well, I just kind of logicked my way to the answer, and this is why. And that's my favorite kind of problems in physics, is when you can just sort of logic through it.
Go through it.
Yeah. Because really, a lot of the problems we do, it's like once you figure out the physics, then most of it's math. And this one, there's like almost, there's really no math unless you count this. So it's like all physics, no math. So that's RL circuits. There is a really hard homework problem that's similar to this, but there's 3 resistors. And I worked out the solution for you because, of course, the
Solutions are posted.
actually this is another one that came out of our old book, so this didn't come out of our current book.
This one or the one you're
It's the
talking about?
homework problem.
Where is it on?
It's on the homework set. It's called 611, and it's a similar circuit, but you can see there's 3 resistors instead of 2.
Mm-hmm.
And so
Same sort of thing though?
similar. It's a
That's
little
different?
challenging because once you get to this, like where the inductor acts like a short, then you kind of have to use. Well, I used mesh analysis, but I don't think you actually need to use mesh analysis because there's only one battery. So there's, it's kind of complicated. This one would be too hard for a test because there's a lot of, like 2 pages of the solution here.
Be the whole
But-
test.
While I'm talking about the homework, the solutions are already posted. You can get, you'll get full points on the homework if you turn in your solutions, and you actually turn it in next week. But the solutions are already posted, so you can use them to study. So you'll already have the benefit of seeing how I solved that problem while you're studying. Okay, so that's RL circuits. We're ready to move on. And I'll say that's about as detailed as we're gonna get. And then our LC circuits and RLC circuits, I'm just gonna kind of tell you the pertinent details and leave the more complicated analysis for your circuits classes. So an LC circuit is a circuit with an inductor and a capacitor. And there's sort of 4 states where this that this LC circuit can go through. And what it does when it's operating is it creates an oscillating current. So we start out in this condition, the switch, you've got a fully charged capacitor, and then you connect it to an inductor. So as soon as you close the switch, that's going to cause current to flow. So you start out and you've got increasing current across your inductor, and so your inductor is going to create an induced EMF to oppose that, and at time equals 0, it'll be so strong that it will stop current flow. And so at this point, they don't show time equals 0, okay. So at time equals 0 it would stop current flow, but then gradually it lets current start flowing. So I is increasing in this loop, until your capacitor is completely discharged. So this picture is the point when all the energy from the capacitor has been translated into energy stored in the inductor, and you've got no more energy stored in the capacitor. Once you hit that position, then, let's see, current reaches its maximum level, and then it says, let's see, capacitor charging.
It's coming out of my
Capacitor polarity reverses.
head.
Hanging a picture of us.
I've never made an LC circuit, so is this just something that happens, or is this something that you're controlling?
What are you talking about?
It says that the capacitor polarity reverses then. The capacitor starts charging up and then
Isn't
I
it-
decreases. So are you?
Is that the
controlling
direction?
that?
It shows the arrows
It does
different.
it on its own.
It does it on its own?
Yeah, because it's like, it's discharging and going to the inductor and then it's pushing back and forth,
Okay.
you know? Like, they just push.
A full circle.
It just does, it just does.
That's what
this,
creates the
where it
oscillation.
oscillates back and forth on its own.
Yeah, the inductor feeds the capacitor, and then the capacitor charges up and then goes back.
I think if there was zero resistance, like ideally, it would have to go on forever.
It would go on forever, but it starts to decay.
Yeah.
Okay. Okay, so once the switch closes, then this behavior just goes until it's burned up all the current through the resistance in the wire. Okay, so so you get maximum current at the point when the capacitor is fully discharged, and then it starts to charge up again and the current decreases to the point that you've got no energy on the inductor again, and then the whole process reverses again. It looks like the current switches direction. So it was going this direction, and then now it's going the opposite direction. So they show this in terms of a period. So they talk about these 4 steps happen in one cycle. So one cycle is the current going one direction, and then the current switching directions, and that's one full cycle. So if you had a problem about this, it's going to ask you, like it asks you like the total time for a cycle. They're talking about it going through all 4 of these steps. And so the oscillating current that you get from this can be described, oh, let's see, I kind of already talked about what it does. I can come back to this in a second. But anyway, the oscillating current that you get can be described with an equation based on the angular frequency. So to refresh our memory on how angular frequency relates to
Yeah.
period. Does somebody remember how angular frequency relates to period?
Like negative 2 pi f or something? Angular.
Yeah,
That's 2
that-
pi f.
close.
2 pi f.
So 2 pi f would be frequency, and then period would be 2 pi over period. So that's angular frequency to period. If you wanted to relate the two, period. And so this is a pretty simple relationship based on the value of the inductor and the value of the capacitor. Okay, let me go back and see if our slides tell us a little bit more information about each of the 4 states that it goes through. So the first thing we saw, the switch closed, capacitor starts discharging, and based on our picture, the current was going
Back into the.
counterclockwise, yeah. And so the current in the inductor starts at 0, and it starts building up current until it reaches maximum current. Once the current is maximum, the voltage across the capacitor is 0, and the induced EMF across the inductor drops to 0. It stops fighting the current once it reaches Imax. Then, the second state, the energy starts transferring from the electric field in the capacitor to the magnetic field in the inductor. So that's what happens at the end of this state. All the electric field is transferred into magnetic field. And then, current, does it switch directions still? So it starts out this way. They show no current here, current drops to 0. It's like the end of the state. Almost need like a simulation to show what's happening as it goes. So current persists, capacitor being begins to charge with opposite polarity. Okay? I decreases to 0 and B equals 0 in inductor. So this is once I decreases to 0. Oh, I guess this makes sense. If you think about it like this, you started out with all the, well, let's see. If you think about positive charges being the ones that are moving, we know they're not, but that's the direction of current. So all the positive charges on this plate are moving in the form of current. And so as all those positive charges move, they're going to basically migrate to the opposite plate. And so at this point, they've migrated completely. And that's when your capacitor plate has built up its charge again, but with an opposite polarity on the plates. And then that explains then why it's going to then discharge. Yeah, it makes sense that it continues because it's like you're connected the two sides of the capacitor, so it's going to want to discharge. It's just discharging through the inductor as it goes.
Yeah, it's like a bouncy ball.
Yeah.
You drop it and gravity brings it down, and then bouncy ball picks it back up, and then gravity brings it down.
So I'm sure if we looked at, I don't have all the equations in the slides here, but it seems to me like this would probably be like a sinusoidal function for the current.
It decreases.
Yeah, it's like a.
You have it in the next.
Like that.
Oh, never mind. I was thinking of charging this charging.
That would be my guess. I'm not sure. I'm not going to officially put that on the board because this is like all I really have us needing is this equation. Like if we want to answer questions about an LC circuit, you're only going to get asked about the angular frequency or the period or something relating to that equation. Okay. And then the last circuit we're going to look at, again briefly, is the RLC circuit. So we put everything together, resistor, capacitor, and inductor. And so that resistor we saw with just the LC circuit creates that damping effect. The RL circuit. So the LC circuit, this is like the ideal case. Ideal LC circuit creates that oscillating current that doesn't decrease with time. And then like an ideal RL or RC is going to have the decay as a function of time. So you kind of combine them together, the RLC circuit, and you're going to see a decaying sinusoidal current. So just qualitatively, that's what we think about when we're combining the R, L, and C together. The resistor is what causes the decay of the current. No, that's what's burning up the current over time. There's actually 3 cases that you can get for your RLC circuit, and their names are utterly confusing. Overdamped, underdamped, and critically damped.
Right.
The one that's pretty is
Underdamped.
underdamped, yeah. It's not, see, I always think like it should be called the critically damped case, but it's not.
Pretty damn.
So these are plots, the uninteresting cases of critically damped and overdamped. Basically, the resistance is so high that it doesn't have an opportunity to even oscillate. It just peters out that resistance on the first cycle, and then it's done. Or sorry, the current. So the one that's actually interesting is the underdamped case. The only equation that we're really concerned with is this underdamped case, and we can plot the frequency of oscillations. Omega is a little bit more complicated than the previous one. Okay, so that's the pertinent equation that we care about. Any questions, I guess, about RL circuits before we try this last example?
So do those, is that an acronym or an abbreviation for RLC? What is it?
Resistor, inductor, capacitor. Okay, and I mean, if it's not obvious already, it's very unlikely that you're gonna do anything on the test with an LC or an RLC circuit because we're just looking at this one aspect of it, the angular frequency, and that doesn't make a very interesting test question.
We're always looking for interesting test questions.
Yeah,
I
of
remember
course.
that.
I can't award like 1/5 of your final grade being like solve for the angular frequency of an RLC circuit given R, L, and C.
Oh, well, yeah, that would be a problem with it. We might be pretty happy about it. Yeah. It might be that
Are
reassurance.
you giving
that-
us those values? No.
That would be my.
Because if you give us those
Like,
values,
if you
can tell us
gave
if
the
it's underdamped,
values, like
overdamped.
I mean, it's just a matter. Like I could ask you to solve for L given omega, R, and C, but that's algebra. That's not physics.
Molest me not with this piddly algebra.
I don't need to test you on your algebra skills. Presumably,
We've done that,
they're
yeah.
up to snuff because you're here.
Calculus makes you do that.
There are those moments though where you just need that little, oh, I can do this one, you know?
Well, I could make it a 5-point bonus question.
Hey,
Yeah.
Oh, look at that.
Like-
Got some
like
cheers
this
on
bonus
that.
question.
I like the sound of that.
bonus.
Cheeriness
And then if
there.
somebody asked, are you testing your students on RLC circuits? Oh, yes, yeah, we
Yeah.
are.
There you go.
Absolutely.
Sure.
Okay. So, what resistance R is required in terms of L and C to give an RLC series circuit a frequency that is 1/2 the undamped frequency?
Is it supposed to say underdamped or really undamped?
I think they're saying in the undamped case, it would be an LC circuit. It's just all kinds of confusing. So let's rewrite it in terms of something that makes sense.
A little fuzzy on the whole damped, undamped thing.
Find R for an RLC circuit such that omega prime, that it's got the prime on it, is equal to 1/2 omega, where omega equals the angular frequency of an LC circuit.
So. Okay.
I mean, the way they worded it is they say an undamped frequency, and so they're kind of saying, I mean, if you kind of like logic your way through what they mean, it's only damped because of the resistance, and so if it's undamped, then there would be no resistor, therefore it would be an LC circuit.
This one doesn't say anything about like whether or not it is like underdamped or overdamped or anything like that. So how would you know to use the underdamped specific one when it just says a frequency?
Because it's more interesting. It's a more interesting case.
I don't know.
But you know, like how do you
honestly-
pick that like specific equation versus when it just says? I mean, yes, an LRC series can have an underdamped, but it can also
Yeah.
have an overdamped and superdamped.
Yeah, but I think it wouldn't have an oscillating frequency if it was overdamped or critically damped, and so they're again like the second piece of logic is if it's going to have a frequency, it would have to be the underdamped
It
case.
doesn't say that it's oscillating though, or like anything related.
Well, I mean, if it has a frequency, I mean,
Unless you're doing something.
like in these cases, it's not. If there's no cycle, then there's no frequency. Like frequency is like cycles per second. And these ones aren't oscillating, so they wouldn't have a frequency. I'm trying to like explain why the book is dumb. If I'm not doing a
Interpreting,
good job, it's because the book is dumb.
interpreting the book.
I just, you know,
But doesn't.
we'll just
even
we'll
the
add to our rewritten
and
problem. Let's see, find our for an RLC
Frequency.
circuit that is underdamped. How's that?
So it says frequency, so that's code for oscillation.
Yeah. Yeah. Okay, so it's like, okay, worst problem ever.
Not on test.
No. No. Okay, so we get the gist, right? They want us to take this equation.
And compare it against half of the other one.
Yeah. And then it's algebra.
Algebra, blah, 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 thing and thing.
Well, there's another reason why it should be on the test.
So, okay, I don't even want to, like, this is dumb. Watch your instructor do some algebra in your physics class. So you solve for R, you got the solution on the same page, so I'm sure you guys can handle the algebra.
Oh.
That's a lot of confidence in us.
Yeah, especially at the end of the term. And
Well, you don't have to do it on the test, so if you can't handle the algebra, that's okay.
you can. I like that term.
If you can't handle the algebra,
If you can't handle the algebra.
that might be a concern for other reasons.
Yeah, it depends what time of day it is.
But in this particular problem,
Yeah,
you won't
no
have to
problem.
see this on the test, so. I'm really
Give it
selling
a-
this lecture to you guys. No, we're gonna learn about stuff that we're not gonna be
It's
tested
not
on,
important.
because I really don't care about it.
So the answer
I
is
just,
don't
it's sort
care.
of, I know, yeah.
This goes on YouTube?
I should really watch what I say when I'm being recorded.
You can edit it down, you know.
I should definitely edit
Next
it.
thing you know, you'll see yourself on a news feed. Physics professor says she doesn't care about physics.
Wait, what?
Wait, what?
Don't put words in my mouth.
That's not what I said.
I think I said
The damage
I
is
don't care about
done.
algebra.
I don't need to test you on your algebra.
Physics teacher says algebra is not important.
Find the logic.
Algebra is
Alright.
dumb.
So that's the end of the lecture. So I have clicker questions on the very first page. You'll notice I got some clicker questions to review this stuff. So that's what's coming up next. But before I do that, do you guys have any questions on this stuff? So let's give this a whirl. A small circular ring of wire, shown in blue, is inside a larger loop of wire that carries a current, as shown. The small ring and the larger loop both lie in the same plane. If I increases, the current that flows in the small ring does what?
I had to think of which way you were going.
Anybody need more time? No? Okay, who thinks that the small ring has a clockwise current caused by self-inductance? Who thinks it has a counterclockwise current caused by self-inductance? Who thinks it has a clockwise current caused by mutual inductance? Almost everybody. Who thinks it has a counterclockwise current? One. Okay. So everybody who voted
Opposing the
C,
change.
somebody who voted C want to tell us why they thought that it's got a clockwise current caused by mutual inductance? Yeah.
I can. I mean, if the eye that's shown is going counterclockwise, then and it's increasing,
Mm-hmm.
then the current in the small ring would want to oppose that. So it's going the other way, going the
Mhm.
opposite
Yeah.
of the first one.
Okay. And then,
And there's two, so I eliminated self-inductance that way.
all right.
That's what I was worried about.
Okay.
Hmm?
The other people who voted C
Mhm.
concur or want to add anything, or
We concur.
you concur?
Concur, Doctor.
So if it was decreasing, it would be counterclockwise.
Correct.
Yes.
Yeah. So have we swayed you, Derek?
I'm still gonna be a non-conformist, but I
Oh,
believe you.
okay. All right.
It's a protest.
Write that on your-
All right, so the answer is straight.
He's-
That shows that conformity, disease, rebellion is secure.
I won't force people to conform.
No, we won't go.
You get an F on the test.
Sure, be different.
But you'll have your
Everybody else
principles. Gotta stand for something, even if it's wrong.
Okay, a current flows through an inductor in the direction from B to A. There is zero resistance in the wire of the inductor. If the current is decreasing, what does that say about the circuit? Too many things to read.
I object.
Well, if the current is deep.
Zero
There's a not enough information one?
Yeah, yeah, it's kind of a weird question.
Not a choice.
It's in the southern hemisphere. It's at night.
Oh, okay. I get it now, because if it's deep. Okay. Hmm.
Isn't this just like the discharging situation where you have your inductor and your resistor in series and the current's still decreasing?
Uh-huh.
But which side of the inductor is it?
Is it
higher potential?
Yeah. Mm-hmm.
Is it because is it like with the little circuit being unattached now? Or does
It's
that?
not unattached.
If you think about it, the case where you open the switch,
Okay,
yeah,
okay,
where the current's falling.
okay.
Mhm.
That's
Okay.
falling.
It's in a circuit imaginarily, we're just not looking at this part of it.
Okay.
It's not just hanging out by itself.
It's not hanging, right. It's more
So it was part of a circuit.
Right, well,
You have
yeah,
to
it
open
was-
the switch in
sure.
order for there to be,
Okay.
there has to be a
Where's the
resistor.
current decreasing?
Greater, and then-
Like, does it change
Well, I
the
mean,
magnetic field? Does it stay
Somewhere.
I gotta guess.
Yeah.
Like above
How
the-
pretty is
But
it?
it's-
So I
it's
know
hooked up for the
some people are
current.
just gonna guess, so that's okay. You guys ready to vote or
Yes.
guess?
Floater gas?
So who thinks that answer A, the potential is greater at point A than B? This is 1, 2, 3, 4, 5, 6. Who thinks that the potential is less at point A than at point B? 1, 2, 3, 4, 5.
Mm.
Over
Any
our
votes for
limit.
C, D, or E? Because I think that was everybody. Okay.
Derek?
So, all right. We pretty evenly split. So somebody who voted for A want to tell us why they thought the potential is greater at point A than point B. Yeah, Hannah, why do you think?
Because if it's, even though the current is discharging in general, it still is like kind of a voltage rise through the inductor a little bit. Or like the potential difference is higher after it goes through because the inductor stores current a little bit. Well, not really stores current, but
Okay.
I don't know if I can like explain it very well.
Well, it stores the potential energy.
Yeah.
Okay. And is there someone who, anybody want to add to that? From the A group?
Isn't it
From
from the
The
A?
18.
Well, the reason why I was thinking A
Getting
would be
fooled.
because that's the way the current's going, so then as it's decreasing, it's obviously higher going around, and then by the time it comes all the way back around, it's been a certain amount of time, so it's decreasing a little bit.
Also, the current
loss.
it
It's a
is
loss, there's a loss going
opposite.
Yeah, there's a
Right?
loss over that,
Mhm.
right?
Oh, yeah, let's answer that question. Which direction is the induced EMF? If I is decreasing, what's the direction the induced EMF?
To the right.
To the, yeah.
To the right.
Yeah, yeah.
Is it to the right? Oh.
Yes.
Because it's trying to oppose the
Yeah,
loss,
opposes
right?
the-
It's opposing the loss,
current.
but if
The
it's,
current.
Opposing the
but,
loss.
but there's zero resistance now.
That's okay.
Oh.
There's a
The wire
loss,
has resistance.
there's a loss across that, right? 'Cause it's-
Right.
So anytime you got decreasing current, then, no wait.
Not approved.
Increasing current, never mind. Okay.
Increasing or decreasing current?
Decreasing current, so if it's decreasing, it wants to oppose the loss. So
Yeah.
what would the direction of the induced EMF be if it wants to oppose the loss?
And the same as I.
To-
And the same as I. Okay, so we got some people saying the same as
I
I.
don't know if I'm right.
Anybody still saying in opposite to I? I mean, we know we're evenly split on these answers, so that's.
I'm not,
I
I'm
spit on your answer.
I declined any more information.
Or would it be to the
Alright, so
right?
I'll draw them again for,
Purposes of decision.
just to remember what we had on the board, so you can see what we had on the board. So if I was increasing, then we said the induced EMF is gonna block it completely, so it's gonna go in the opposite direction.
Mhm,
And if it's
mhm.
decreasing, it goes in the same direction.
Yeah.
Because it wants to oppose the loss.
It adds to the loss.
Yeah, so it adds to, okay. So now who thinks that the EMF is
Oppose the
going to
change.
the right? The
Wait,
left.
what?
Your left.
You're confusing me.
Your left.
Also the same?
Going this
So-
way.
Oh, yeah, it is.
Yeah,
It is.
yeah.
Okay,
Yeah.
anybody think it's gonna go to the right?
No.
Okay, fair enough. Okay, so we
that
agreed
means we
that
regroup.
I enjoyed the
reduce
group
the
this
EMF
time.
this way.
Couldn't help it.
Confusement.
And that's,
So
so
your
it's,
voltage is going from this direction. What does that say about your voltage values at B and versus A? So it's gonna
Plus it B.
less at B and
More
higher
at
at
A.
Or
A.
they-
Which means A group is, of course, the winning group.
A team
Woohoo!
from Hannah. Just reiterating what Hannah said, I'm still being partial judge. Anybody from the B team wanna weigh in?
He said he converted, so.
Yeah, I think I had it backwards.
Oh, 2 converts. Anybody left from the B team?
I have to think about it a little bit more.
Okay.
I'm not ready to.
Tell you, my original thought was that it would, yeah, the EMF was gonna move with the current so that there would be a higher potential on the right than there would be on the left.
Yeah, that's what I'm.
That was my original thinking.
Okay.
What changed? Because now you have that going to the left.
Yeah, it's still moving that way.
The thing that helps
you
you kind
think
of clear that
about-
up is if you think about it like it's
Lower.
a source now, because since it's decreasing, it's adding energy to the circuit, so now it looks like a voltage source. So where there's current coming out, that's the positive side. It's got a higher potential than the negative side.
Oh, okay.
Or like the pump.
Yeah.
If it's
Yeah,
pumping,
yeah.
if it's pumping water uphill, then this would be the bottom of the hill, and this would be the top of the hill. Okay. I don't presume to sway everybody's view. The correct answer is A. Okay. Next one. A steady current flows through an inductor. The current is doubled while the inductance remains constant. The amount of energy stored in the inductor does what?
What's the equation for this?
What's the equation?
Yeah, what's the answer like?
That's fair. I've told you guys you don't need to memorize stuff,
It's
so.
squared in there, okay.
Okay, everybody ready to vote?
Mhm.
Okay, who thinks it increases by a factor of square root 2? Who thinks it increases by a factor of 2? Who thinks it increases by a factor of 4? Almost everybody. Who thinks that it increases by a factor that depends on the geometry of the inductor? Who thinks none of the above? Okay, those of you who voted C. And anybody want to tell me why they voted C? Do I really?
I squared.
I squared 4. Okay.
4, yeah.
Okay, so the correct answer was C. Any questions? No? 30.4. An inductor and a resistor are connected to an EMF as shown. When switch S1 is closed, a current begins to flow. The final value of the current is what? Hannah's giving hints. Don't worry, I was too. When I first read it, I'm like, oh, is this something really complicated or not?
Oh. Yeah.
Okay, so is everyone ready to vote?
It's kind of
I
weird.
think Hannah gave it away.
Yeah.
Maybe not.
Nice one.
Well, we'll see. Who thinks that the answer is A, that it'll be proportional to RL? Who thinks that it'll be proportional to R over L? One vote. Who thinks that it'll be proportional to, let's see,
Wronski now.
C, directly proportional to L over R? Who thinks it'll be directly proportional to 1 over RL? And who thinks it'll be independent of L? A whole lot of people. Okay, so Hannah, hint giver, tell us why you chose E.
Because just like before, after current has been flowing for a while and it reaches a steady state, it acts like a short, so it really doesn't matter what the inductor value is. It's pretty much acts like a chain wire.
Yeah, yeah. So it's like it's not even there. What would the value, so that was what we called Imax. So what would Imax equal? Yeah, just E over R. So if they said directly proportional to 1 over R, then that would have been also correct. Any questions on this one? Okay. I don't know. When I first read it, I was like, does this have something to do with that time constant? I'm gonna have to calculate something. Yeah.
I looked at final value and I looked at independent of L and then I looked at the circuit and then I rolled my eyes at myself.
Well, there was another question I'm pretty sure I didn't pick that was horrendous that asked something related to time.
When time
And
will affect.
it had to do with the inductive time constant. The wording was just like, what? I don't know. I don't think I chose that question. Let's see. Maybe I did. Okay, this one does actually ask about time. We'll see. This one's really confusing. Let's see if we can answer it.
Yeah.
Let's see. I was also late, so I'm trying to remember. Okay, so initially switch S1 is closed and switch S2 is open and current flows through L and R. When S2 is closed and it doesn't say this, but when S1 is opened, the rate at which the current decreases is what?
The rate.
Oh.
Hmm. Okay.
Sort of changes the meaning of things, we don't have that. Okay, anybody need more time? No, okay. Who thinks that the current decreases, or no, the current remains constant? Nobody. Who thinks that it increases with time, that it decreases the rate?
What?
The rate at which it decreases increases with time.
No.
No.
This doesn't even
No.
sound right.
It's hard to say it. Okay, who thinks that the rate at which the current decreases with time? A lot of people, everybody. And then not enough information. So what's the graph of how it decreases with time?
Canyon exponential.
Down slope.
Yeah.
Exponentially.
So
So it
at the beginning,
decreases with-
it's decreasing rapidly, right? The rate is sort of like a slope. So it's got a big slope, so it's decaying rapidly. And then over time, it's decreasing slower. So it's decreasing at a decreasing rate. If the graph looked like this, then you could say it's decreasing at an increasing rate. But I don't know that I've ever seen that in physics, like a real world problem. Maybe in a math class. I don't, this behavior doesn't happen very often in
When you
nature.
throw a ball,
Well, it's
That's
trajectory.
true. Sure, that's true. You
Projectile.
talked about
Projectile gravity
the
problems.